Good afternoon. Hope everybody had a great lunch. My name is Sean McDermott. As you can see, I work nowhere. Currently an unemployed independent researcher. Yeah. But I was working at Microsoft Research before at Harvard, so I do have some experience. Today I'm going to talk about this project I've been working on in my part-time while taking care of my kid called Tangible Abstraction.
Funny name for a kid.
The kid's not named, but yeah, maybe I should rename him. No. All right, so I'm just going to get started with the content. Okay, but first a little bit of context. Okay, our goal, hopefully, of the whole PL community is make better programmers, right? And there's multiple ways we can go about doing this. You know, we can just create programmers with a lot more talent, you know, like the archer who can shoot anything, even though it's really just a normal bow and arrow, and they have no real magical power or anything, but they can still, you know, hit a target from like 100 miles away, right? Or we can create a programmer super serum, you know, and you know, make our programmers strong that way. Or we could just, you know, create robots that program for us, right? Or we could, you know, augment ourselves with some kind of, you know, special programming environment. And, you know, I'm not really talented, so this is sort of out of the way for me. I mean, other people probably can do better. And, you know, I grew up in the 80s when, you know, doing drugs was bad. So that one's out. This is really for the ML people, not for us. So we're not going to do it that way. So this is it. Right? You know, how can we build our super augmented programming environments to make us better programmers? And so sort of the focus of my research is sort of, you know, how can we do much better than we're doing now? Okay? So one of the big problems with programming is this mental simulation, right? So whenever you're writing a program, you're writing the code, but you're thinking about what the code is doing at the same time, right? And when you read the code, you also have to sort of read these instructions, which are probably too small to see, but you know, this is just the code for Quicksort. Right? And you know, it gets really confusing because the code is like here and it's specifying something, but each time you read a statement of code, it sort of elaborates something in your mind. You get this mental model of what's going on, and it allows you to write the next instruction. Right? But this is pretty, you know, a pretty hard process. And you know, you can actually, you know, we can do things like showing examples and you know, showing how the values flow for examples, but you know, it's really quite unsatisfying. Okay. So a lot of the work in PL is, you know, create programming languages that are a lot easier to mentally simulate in your head. I don't know if anybody is familiar with Kodoo. It's this Xbox game programming environment. But you know, it's like, I saw a tree, I moved towards the tree, right? You know, it's pretty easy to simulate that, right, in your head. Imagine I see a tree and I move towards a tree, right? And this is okay, but there's a lot of problems that don't really fit this style of programming, and there's a lot of, you know, it's just the code is complicated for a reason because, you know, we do a lot of things that are hard to sort of express very concisely. So a way around this problem is to get immediate incremental feedback on what you're doing, right? And one way to do that is to use a REPL, right? REPLs are good. You know, you type in an operation, you know what the inputs are because you have the values right there, and you know what the output is because as soon as you hit return, you get the value of your operation, right? That's great. And you know, a lot of people like working inside REPLs, but it doesn't work really well with abstraction. So at the top level, you get feedback. And then you know, I start writing this if statement here, right? If A is greater than 10, bigger, else smaller, return. Right? I don't get any feedback for anything in here until I use that code. It types bigger when I actually finish the whole block of code. And then the other branch never gets executed at all. Right? So REPLs aren't great for, you know, programming with abstraction. They're great for playing around with APIs, and they're great for, you know, doing examples. But you know, as soon as you get down to writing, you know, more abstract code, they're not as useful anymore. Okay. So to fix that problem, we have this thing called live programming. Now, some of you guys were at the live programming workshop on Monday, or Tuesday. Tuesday. Right. And what this does is, okay, well, the REPL is a top-level environment, gives you values, produces values. But what if you have abstract code? Then we can sort of project examples, or we can project concrete values on top of that abstract code and visualize that then in real time, right? So we have, I don't know, Brett Victor's stuff is pretty canonical in this area, where he, here's the loop, and you can see each iteration of the loop as a table, right? This is the learnable programming essay that he did in 2012, and a Python tutor from Philip Guo, and this is more Brett Victor stuff, and you can see more context over here. So live programming is one way to sort of get more feedback on our programming experience, but there's some problems here, right? One is, setting up the concrete example or context often is not worth it, right? I want to write code. Now I have to sort of inject real values into my program, and if I'm having trouble, that's great because, I'll take the time to do that because this code isn't working the way I thought. I'll inject some values and I'll program in that context. If I'm just writing code as normal, right, having to go and inject values each time into my context when I'm writing the code to make sure that I have feedback on values is kind of annoying. The feedback can also be distracting, right? I mean, some programming, some of the live programming environments, you type things and you keep seeing things flying around. It's not actually helping you write the code. It's just kind of, it's distracting your focus, right? You have this abstract model in your head and you see these concrete values to the side that are constantly changing in ways that aren't necessarily very meaningful to you. You just kind of tune it out. And the feedback can be mentally expensive to process, right? It's like, if I was doing Quicksort, I'm writing my Quicksort code here and I'm seeing all these values here, these numbers, right? I'm doing partitions and sorts and partitions and sorts. And it's great for verifying that I'm doing the correct thing, but it's not really great for figuring out what the correct thing to do is in the first place. Because, first of all, it's like, they're just numbers on the screen, right? And I have to take time to process it. And if I have the abstract mental model in my head is much quicker to access. And these often have to do with the gaps between evaluation and execution. If anybody's familiar with that HCI work, was Norman?
Don Norman, yeah.
Yeah, Don Norman. Okay, so a better way to do this is through direct manipulation. Well, not a better way. It's one another way. Direct manipulation is you touch the things that you want to manipulate directly. But actually, I'm going to look at something a little bit less powerful than direct manipulation called tangibility. And I'm making up this word, so it's not, probably there might be a better word for it, but I'll go tell you why I went with this word in a second, right? So in this sense, tangibility is like direct manipulation, except it can be acted upon via, okay, we get rid of physical, we get rid of reversible, incremental actions that receive immediate feedback. And actually, when you think about a REPL, you have tangibility, but you don't have direct manipulation. So a paper, so I use the word tangibility because there was a paper in 2007, 2009. Maybe it got published in 2009 and it started being shopped around in 2007. Conno Elliott did this paper on tangible values, where he takes, he's a big Haskell guy, but he's got all these, crazy ideas that are pretty wonderful. So what he does is he takes your, Haskell expressions and he empowers them with values. And if you don't know what the value is, you actually get a slider or something. So as you're composing your Haskell program, you actually have values, accessible values, and you can actually play with those values and see how they work in your compositions. And then you can compose those together, which reduces the range of values that you can access, or binds values, and then you get sort of a combined composed concept. So that's cool. I'm not going to actually do that. I'm doing something else, but it's really inspired by this work. So I'm going to tackle the problem of abstraction directly, rather than just put values into my code. Okay, abstraction is a hard problem. What can we do with it? Well, how about a REPL for an abstract representation, right? We have REPLs for concrete values, right? But we don't have REPLs for abstract things. And what does that even mean? So instead of manipulating concrete values in your REPL, you're going to be manipulating an abstract representation. I'm going to be changing the abstract representation directly to sort of express my program. This is why we call this tangible abstraction. So now the next question is, what representation do we use? Well, we know that patterns can match data. I mean, pattern matching, you express these patterns, and they match your data, types, regular expressions. We're actually going to focus on regular expressions here. So I don't know if anybody's familiar with a regular expression. There's sequence, ABC means this comes after this. And then there's a disjunction, A or B means that it's either A or B. The pipe symbol. And then the clean star is 0 to many repetition. And the question mark is just optional. Right? Either it exists, either it's A or it's empty. All right, well, I had a problem, so I used regular expression. I mean, people don't like regular expressions in general. They think they're kind of hairy. But we're not using them for recognition here. We're only using them as representation. So don't worry. So here's an example. We have the regular expression AB star C. Now, AB star C can represent a variety of concrete data, right? It can represent A, B, 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 C, A, B, B, C, or AC, right? Okay? And we can operate on this regular expression to swap. Let's say we want to swap the A and B, or the A and C that are in the expression. Can everybody see this? Just fine. The size is okay. The people in the back. The people in the back might want to move a little bit forward if you can. I'm going to start doing the demo just because you might be too small. Right? So we do this swap, and then we turn A B star C into C B star A. And consequently, all the concrete values that match A B star C can be operated on by the swap by doing the same thing, so that they match C B star A. Okay? So we just operated on an abstract representation, and we got the concrete transformations for free. But not only did we just operate on an abstract representation, we got this out of it, and we know what these look like now. We don't even need to see these. We know they're C B star A. Okay, so we got our feedback. So here's a more complicated example that uses a bunch of operations on C D star, right? We take the D star and we say, well, we're going to change that into we're going to change that into D star D, right? Because you can do that with regular expressions, except D star could be empty. So there's one path that says, oh, you can't do that. D star is empty, right? And if it's not empty, we're going to swap C and D like we did in the example before. And then we're going to take this D here, we're going to push it back into the regular expression D star. And over here, if we have C and it's empty, we're just going to insert an empty D star into that so that these two things are the same. Right, now we have a function from C D star to D star C. Right? However, this is not ideal. This is not tangible. This branch is really annoying. Have you ever played with a Rubik's Cube and have it switched into two realities, into two possibilities? No, you haven't. Everything is a line. I manipulate something, and it's in one state. It's not in two states. Right? So we have to get rid of this branch. It's not tangible if we can't get rid of this branch. So here's the idea. We're going to linearize this tree using color. Right? We're going to make this branch red and this branch blue. And blue and red together are just going to be black. We're splitting black into blue and red. And we're saying, well, if we're in the blue channel, we're going to call them channels. If we're in the blue channel, we have C. And if we're in the red channel, we have C, D star, D. And since they're separated, we can put them together. Right? We can put them side by side, because there's either red or blue, right? And we can just filter out the one that we don't want when we operate on the other. But we can even merge those representations so that, well, there's a blue C, but it can actually be combined with the red C, and so we can have a black C in our representation. So when we do this pop R on D star, we get D star D red. And we have two channels, red and blue. And we don't see anything blue here because the blue C that we would have seen combines with the red C easily, right? So blue represents an empty case where D star D doesn't exist. And then when we filter it out, with the red filter we see D star D, and when we call this polarization. When we polarize it, and when we polarize it with the blue filter, we only see C. That means we have a representation that expresses both sides of the branch, but we still have a line. Now, when we execute swap on CD star D, right, we're doing that on the red channel. We can't do that on the blue channel because there is no D to swap with on the blue channel. Right? We first sort of polarize the representation to CD star D red and C blue. We execute the swap, right? D star C and a blue C at the end, and then we reconsolidate the representation, right? And we have D star D, D star C out of it, okay? And then the rest of the stuff occurs as the same way, except when we do empty right now, we're just taking this red D star and we're adding the empty blue D star on top of it to create the black D star. And we don't actually even have to specify. We just point at the red D star and say, I want that to be black, and it will add the empty D star automatically for the blue channel. Okay, so that's the gist of it. If you don't understand very well, it's fine. I'm going to go through plenty of examples. And I think, yeah, let's just do examples now. Okay, enough slides. We're doing a demo. Okay, so let me get out of here. No, I don't want to use, what the heck? Oh, I'm hitting function. I'm sorry, I don't know how to use computers anymore. It'd be weird, like when you're just giving the demo during your talk and it just decides at that point not to work anymore. It would be very, very unfortunate. Okay, so this is my demo. So it starts out as empty. We can create a new sort of procedure. And I'm going to go with partition. So we're going to do Quicksort. And you know why we're going to do Quicksort? I was told by an industry representative that programmers implement Quicksort multiple times a day. So we're doing Quicksort.
Doing interviews only.
Well, yeah. Of course. It's a very important problem in computer science that people solve often. So we're going to start off with the partition function for Quicksort, right? And type in partition here, and I'm going to specify what that input looks like. So we go A or A, B star. If somebody can't see the projector, just move up a little bit. There's plenty of seats open. If people could move in a little bit, if people want to sort of easily, sit up. I don't want anybody to hurt their eyes, and I can't really make this bigger. I can make it bigger temporarily, but my menus prevent me from making it much bigger. Okay? Because they appear at the bottom. So I'm going to set this up as A or B star. So we have a string. It's either has some kind of A element or B element. And these A or Bs are variables. So they don't exactly represent A, or they're small a's. So they represent something that's bound to A. Okay? Done with that. Right? So I'm going to implement this partition function. We're going to start off with a loop. So I didn't talk about loops in my previous example, but loops are very simple. And we'll get there when we actually have to do the backwards loop. So it just changes the color to green when we do a loop, because we're going to loop through all the values of our A or B star. Right now we are going to do this popple, which gives us the first element. And like before, we split into these red and blue channels, right? The blue channel being completely empty, and the red channel having everything else. Okay? Now, you see the sort of the railroad tracks here tell you what the channels mean. Right? Right, now we're going to have to sort of divide our OR statement using an operation called fork into pink and orange channels. This is getting very colorful. And if you're colorblind, you might not actually get this, but because the colors are too close, right? So fine. The first thing we need to do is get this. We need to create a B star to capture all the B's. So we have this operation called lift. Lift is working with the loop to create an empty B star at the beginning of the loop and then to push the B into that empty B star at this point. And the reason why we don't create the B star up here is we want to avoid pre-commitment. A tangible representation doesn't require much pre-commitment. You can basically say, if I had to create this B star up here, I would have to plan all my instructions down here. And what we're aiming for is something that's a lot more fluid and on the fly than that. Something that doesn't require much thinking because we're taking out the mental simulation from the programmer. So we want them to feel like they're just playing with a Rubik's Cube. Okay, now I need to move this A to the beginning of before B star, and I don't have that right now, so I'm going to have to create a new procedure. So we're just going to create another one here. We'll call it slide. And this is the one I implemented on the slides in the previous example. So we're going to take CD star, and we're going to convert that into D star C, right? So it's done. So we're going to pop R that, do the swap, push that into the D, and then add the empty D so that it's the same on both channels so that we can have our merge. And then I'm going to return. Okay, we're done. So what does this mean from an execution perspective? Let's go through and let's actually trace examples here. We have a lot of examples, but we only need this one here, right? So we start off, at the beginning of the function, we have C2, D0, D1, D3. So you can see these little subscripts here, mean that these are different Ds, right? And then we go to the first one, and we pop off the last D. So this last D is segmented away from this D star here, and then we swap C and D. And then we we push D into this D star here, and that's it. We have our D star C representation. So as you can see, the mapping to the concrete execution context is very well defined. We can even check out the blue channel, which is just when D star is empty here. So this is C0 and D star is empty. So we do our first branch, and we wind up in the blue channel. Okay? And we skip all these red channel operations because they don't apply to the blue channel. Our next operation is just adding an empty D star to the metadata of the concrete example. Okay, and that's it. So let's go ahead, and I'm going to add this to the menu. We go back to partition. So now I can call slide on B star A, but remember it was defined in the other direction, but it turns out that regular expressions can be reversed very easily, so it automatically adds the reverse of all procedures you added to the system so that it works that way. So now A is at the beginning, and we do the same lift that we did for B star. Okay, and we can see that we have the solution now. A star, B star is kind of what you want with a partition. When we have this red thing over here, right? We need to get rid of this, but we established the loop over here, right? This is the state that you need to re-enter the loop, and this is the state we have. They match up perfectly, so we can do our unloop. Okay? And that, if you look at the railroad track, you can see, okay, we've gone here, we split into this purple and orange, or pink and orange channels, and then after we do our lift, we don't have any distinction between the two channels anymore. We're back to red. And then when we unloop, we delete the red portion and go back up here, and all we have is the blue channel left. All right, so loop is just delete the loop invariant. And that's it. And we don't need a looping representation for our abstract representation. We just need very well-defined semantics for this unloop operation. Okay, now we can return. I'm gonna have to reduce the screen. Okay. So we can go through an example. Let's pick one that's interesting. Okay. So here is where A or B star, the concrete mapping is A0, B1, A2, B3. Okay? And we just generate these automatically using the format of our input. Okay, so we look at the first one. We add our empty A star and B star because of the lift operations. We pop the head element from the representation, and we decide whether we're in the pink or the orange channel. We're in the pink channel because it's A. This A is pink, and this is an A. Right? And then we go to the next one, which is our slide reverse. And then we do our lift, which puts it in the A star. Okay? And then we go back up here because we're looping. We do the pop again. This time we're in the orange channel. And then we just do our lift, and then we're done. We start and we do another pink channel again, and another orange channel. And then finally we come back up here and we do our loop, and then once we do our pop, we find out we're in the blue channel. And when we're in the blue channel, the center disappears, and here's what we have. We have something in the form of A star, B star. And that's partition. And with that, we can do Quicksort. I'm going to add that to the list of stuff. And we're going to do a new thing here. I should be using the mouse, actually. That's why I don't have the mouse. All right. Quicksort. And this time, we just say A star is our input. Okay. Done. But Quicksort's recursive. And I don't know, in Scala, if you have a recursive function, then you have to specify its output. Right? So we're going to specify its output here. Right? Which is this little thing. And this little hat here means that it's sorted ascending. So if you can look at it, maybe I can expand it just for a while. Oops. Right, this little hat it just means it's like an A star, but all the elements inside it are increasing. Okay? So let's go ahead and implement this. We're going to do a popple. We get this red and blue channel. Right, now we're going to pivot. Right, this is an interesting operation. It takes the value of A that we're pivoting on, and it says, well, every other A is going to be divided into something that's less than or equal to this A, or greater than or equal to this, or greater than this A. Right? And so we can see we have, this is A1, and these two, this one is A0, comma A2, but we can turn that into a division where we have A0 or A2. And now, sorry, I shouldn't pause. And now that we have this A or A2 star, right, we can use our partition method that we just defined. Right? So we have, we can partition it this way. This isn't going to give us what we want unless we want to go in the other direction. Or we can partition it this way and puts the A2s at the beginning. And actually, okay, that's another point here. There's two ways I can call partition at this point. Right? One is I can call it with A0 or A2, or I can call it with A2 or A0. Right? Because disjunction is not ordered. But the system notes the ambiguity and just gives you two choices. One for that configuration, one for the OR clause in that direction, and one for it in the other direction. So now we can just select this one, which is what we want. So we get A0 star or A2 star. And then we need to get A1 into the middle. So we just use slide. Right? Now we have A0 star, A1, A2 star. And then we just do our recursive sort. Oh, I have to add it to the list first before I can do that. Sorry. Now we get here, we can sort this one. And we can sort that one. And now we're pretty much done. But we have to sort of massage the representation to get the output that we want. So we do a pusher, and we do another pusher, or push out. And there we are. But then of course it's red, and we have to consider the blue channel too. And the blue channel, remember, that was the case where it was empty, right? And of course, but we can add that. I have to make it smaller again. Sorry. So but of course, anything that's empty is already sorted. So we can add an empty blue sorted A list, right, to the representation, and we can get that for free. Right, now we have our output, we just return. Okay, that's Quicksort. Make this even smaller because I need more space. I'll expand it again, don't worry, in a second. Right, so now let's try it out on an example. Let's see, something like this one maybe. Okay. So I'm going to go ahead and make this bigger. Oops. This one. Okay. So now we start off and we pop off the first element to be our pivot. Then we divide our pivot. This doesn't actually have the subscripts in it because the runtime representation just erases all of those. And then we do the partition. Right? And the partition gives us, okay, these ones are less than 4. So I don't know if you guys can see the subscripts very well, but this is 1, 2, 0, and 3. Those are less than 4, and these are greater than 4, 5, 7, 10, 9, 6, and 8. And that's the partition function that we just implemented before. Okay? And then we do a slide to get it into the middle, to get the pivot into the middle, the pivot element into the middle. Right? And we can see, okay, well, now it's in the middle. Yes, it's in the middle up here too. And then we do the recursive quicksort. So this one sorts this one. Before it was 3, 1, 2, 0, and then now it's 1, 0, 1, 2, 3. Right? And this one does the same thing for the other side. And now you can see these values are sorted. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? But of course, we can't stop here because we have to we have to massage the representation to actually get what we promised. So these breaks between them are meaningful and mean that this is not equivalent to that. So we do a couple of pushes, and that's it. We have our A. And if we were, why does it keep doing that? Stop. Because I keep hitting that. If we want to look at the empty case, case is here, and we can see, okay, we do the pop here, and we're in the blue channel, and then we just add an empty one, and that's it. Right? And those are the only two cases to consider for Quicksort. Okay, so that's it, Quicksort. And if this representation is, means that, well, not only we know what each step we're doing, we're only looking over here really. This stuff we're not really looking at when we write the code, even though it's useful for understanding. So I can do another example. So one of the interesting things about this system was that when I did it, I learned some new things about sort of what I was doing. Right, one was this sort of, if I take all the A's out of an A, B star, what do I get? So I call that sift. And you can say, okay, this is A or A, okay, A or B, A or B star. Let's go back to one. Right. I'm going to do something here. I'm going to put this in Zen mode. What Zen mode does is it focuses on the representation and doesn't focus on all this other stuff here. Because when you're actually using this system, you're just manipulating this guy over here. You're not really concerned with this because you don't need to mentally simulate the code in your head. Right, so we're going to call this sift. And the first thing that we do is we loop. And we're going to extract all the A's out of the thing. We're not going to do a partition. We're just going to capture all the A's in the representation, at the head of the representation. Okay, so we do a popple. And remember, I'm in Zen mode, so I'm not seeing the intermediate states. We're just dealing with something. We're taking it apart. Right? Now I fork the head disjunction. You see now we have a red channel, we have a pink channel, and an orange channel. And I lift out the A's. Right? And I'm not going to lift out the B's. Instead, we're just going to unloop here. Right? The purple channel can unloop because it's only AB star, and that's what we specified when we looped, right? And that's going to take out the purple channel, which means that the orange channel is the only channel left, and because orange channel doesn't have the purple channel anymore, it's just going to default to the red channel. Okay. So, and then I'm going to turn this into an option, right? So that it's black, because we can only return things that are black. Black channels, the root channel, right? And then we return. Now, think about this. If I took all the A's out of the head of an AB star, what would I get? Well, that makes sense. I would have a B, or I would have nothing. I would have a B and more AB star, or I would have nothing. That's where the option is here for. Right? No type system that I know of will give you this. Even Haskell, even Agda, even Idris. Right? I mean, it's something that just doesn't show up. You know, it's incredibly useful. There's another one we can do here. I'm going to activate sift and do sift back, which is basically going to take the representation that we wound up with last time and flip it around and taking out the B's instead. So A or B star. All right. So this is what we returned in the last function, but we reversed it, right? Let me make this screen bigger again. Sorry, guys. We're in Zen mode, so I don't have to worry about. I don't have to worry about running out of B space. All right. So we have this thing called sift back. The first thing we do is we get into the operations. The first thing is we have this operation called poke, which is just for options, and draws out the epsilon and the case where it actually exists. Right? So I get another disjunction here. Okay, and then I can recursively call my sift function to draw out all the A's. Right? That was the function we just implemented, or draw out all the B's. Right? And then we can poke this guy here. And we can unloop. No, we don't unloop. What are we doing? Oh, we can, yeah, okay, sorry. We can take this last B over here in the orange channel, because the orange channel ignores the pink channel, right? So these two, in the orange channel, B star is just B star B, so we can take this B and we can push it into this B star here, right? And then we can make this an option. Now we only have the red channel left and the blue channel, and we can add, we get our empty stuff for free as before, and we get this one for free too, because it's empty, right? Now, this is interesting because if you look at a Hoare partition, Tony Hoare's original partition when he defines Quicksort, all he was doing was drawing out all the A's, and he was drawing out all the B's drawing out all the A's from the front and drawing out all the B's from the back, and then if anything was left, he would just swap the A and B that were in the way, right? I guess we can return, right? Let's do. Let me reduce the. So let's look at something that's trying out all the B's here. Okay. So we look at this, and of course there's something there. So it starts off. Everything's an option, but of course there's something exists, and then we call sift on the B, and we get BBA, and something still exists, and we turn that into an option, and that's it. We're done, right? So actually, these functions, sift and sift back, don't actually manipulate any of the data. They don't call swap. They just massage the data into a certain representation for other representations. And now I'm going to add that to our list of functions that we're using, and I'm going to call new again. Size back up. We'll call this our partition. A or B star. Okay, and we're going to do a loop. And instead of calling popple or popper, we're just going to call our sift function directly to extract out all the A's at the beginning of this AB star, right? And we're going to do the same at the back. We're going to call sift back rev, because it's reversed, to draw out all the B's at the back. Okay, now if anything is left, we'll call poke to figure out if anything is left. Then it's in a red channel, right? And the blue channel is nothing is left. And we can swap our A and B. Oh, I made some mistakes here. I actually could go back and do. I have to lift these out first. Then I can call swap, right? So I've lifted out those A stars and B stars so that they're outside the loop, so that when the loop executes, we don't lose everything. We start again with the stuff that we had before, right? And then we swap. We do the swap of B and A, and then we can push. We can push the second A into the first A star, and we can push the second last B into the last B star, right? And then unloop. So I make my thing smaller again. And that's a Hoare partition, 20 Hoare partition, right? So now the partition we expressed before is a simpler one called the Muto partition, which is easier actually. You can say it's even simpler in code. Right? I guess we can look at the two ones here since we have it. Right. So that one is very simple. It doesn't require two complicated auxiliary functions, and this one is even with the auxiliary functions, it's much more complicated. And they produce the same output, I believe. There's a way of implementing partition the wrong way that produces the wrong, but does partition semantically correct, but it will reverse the partition if they're already partitioned. So, so we have a second way of implementing partition, and we could use this in Quicksort too. And it's just interesting, to see all the sort of the real representation that's involved in implementing these things. What do we make for time? See the clock when I'm in full screen.
13 after.
13 after, so I have about 15 minutes left.
Right. Yes.
All right. I think this is a good stopping point then for me just to finish off my slides. I have more examples actually. The other ones I have is like something like reverse. You can do reverse. You can do rotate. You can do the Dutch national flag partition if you know what that is. These are interesting things. It's limited though. So let's go back to the slides. So demo recap. We have abstract feedback that replaces concrete feedback. I did show you guys how this executed, but the thing that I'm using to sort of, judge, the thing that we're using to write the code is that abstract representation. You don't, even the concrete representation, it does exactly what the abstract representation says it would do, right? No mental simulation of the code is needed, right? None. All those operations with obscure push R, push L, pop R, pop L. Right? I never had to type those in. I just selected the representation I wanted from the menu. They were not needed for actually writing the program. There's no fancy type checking or code analysis or whatever. Right? One of the problems is when you have a really highly expressive type system, you get in trouble when you start merging, or something. Right? You get to exponential, cases really quickly, but here there's none of that, right? All we're doing is we're manipulating the representation directly. So we don't actually have any fancy algorithms going on in this system. We linearize the branching and looping structure with color, which works out really well to sort of create a linear representation of an abstraction. And we have operators that don't require a pre-commit like lift. Otherwise we would have to sort of plan ahead. Oh, we're going to this loop is going to need an A star and B star, empty A star and B star to push into, otherwise we'll lose it on the next iteration. Okay? Now there are some challenges here. Programmers must manually manage their abstract representation. Again, we don't have any merges, but on the other hand, that means that the programmer has to do all the work. So in our whole partition that we did the last thing, right, we had to sort of do our lifts manually to say what we wanted the loop to, sort of preserve on each iteration. And then we had to push our B's and A's into these A stars and B stars. Right? Normally you wouldn't think about doing that in a program, it's already there. The A is next to the B, it's fine. But we actually have to push them together. And if you think about it, it's not so bad because we don't have indices. We don't have I and J. The indices are implicit in the form of the abstract representation. And push L and push R and these other functions in pop R and pop L are sort of like managing the indices that you would otherwise be doing I equals I plus 1 or I equals I minus 1. So we haven't, basically we're able to do one-dimensional discrete problems like quicksort, reverse, bubble sort, or all sorts of sorts, rotate. But we can't do, it's difficult to sort of expand this technique to sort of deeper kinds of values, like a 2D picture. What's the abstract representation of a 2D picture? Anybody know? I mean, somebody with theory probably knows. I don't, because I was never able to sort of figure it out. Right? Even a binary tree is difficult. You can describe it with a grammar, but it requires forgetting what was above you when you're traversing it, and physical simulations, et cetera, et cetera, et cetera. Operations must have meaning in the representation. Now, this is actually a very complicated requirement. You think about what A plus B means. How would you visualize the result of A plus B? Depends on your representation. It could be just taking something B and something A and stacking them on each other, and this would be A plus B. Or it could be navigating from the left side of a box to its right side, and the left side is A, and the B is width, and you get some representation. Here I don't actually need to know what A and B are, right? But even addition, you get complicated in the sense that you have a lot of things that it's too generic. You need something more specific than addition that involves addition to sort of have a nice representation, a nice sort of definition of how it changes the abstract representation. And if you have something like A times B, it's much more complicated. And I mean, I don't know. Do we think in abstract mental models, or do we think in concrete mental models? And we think in a bit of both, right? So the challenge is, can we replace all concrete models with an abstract model? Probably not. How would they work together? How will they coexist? And I don't have a good idea of how that will work yet. Okay, so I reached the conclusion slide. We use tangible expressions to program real examples. A real example, maybe one, Quicksort. But it's a start. And yeah, you can use this for programming interviews, right? Because they're all one-dimensional discrete problems anyways, right? So maybe I can market this off to people, looking for jobs so that they can ace programming interviews very easily. It's going to be a challenge to bring tangible abstraction to programming in general, if it's even possible at all. But I bet that a lot of these techniques can sort of be used in hybrid systems, which is probably where the general work will go. Okay, and that's it. I'm ready to take questions. I think we have, 10 minutes left? Yes? Yeah, 10 minutes.
So in slide, help me make sure first that I understood what it was doing. So I think you had something like A D star, and you move the last D before the A.
Let's just go there. Yeah, okay, so slide is a bit weird. It's a bit of a, you don't really need it if you're programming in a procedural language, because all you can, you know, it just handles the case where you're swapping the same index sometimes, right? So what it's doing is basically swapping out, let's go higher. Right. It's taking C and it's swapping it with the last D, right? And normally in a procedural language, you just have I and j in the right locations and you do the swap. But since our abstract representation doesn't actually expand out the D, or we don't want to expand out the D all the time when we do slide, we create this auxiliary function to do it for us.
So I guess what I'm wondering is your claim is that I can understand this without looking at the individual instructions.
I can say, I'm saying you can write this without looking at the individual instructions. Now, understanding is different, right? I mean, understanding is like, well, it depends on, let's go back to Zen mode here, which it hides everything in between, right? You know, all I know is that I'm taking something that's CD star and producing something that's D star C. Now, the representation doesn't tell you if you're using operations like delete and adding new elements or whatever. It doesn't tell you, you know, if it's an actual permutation. The only reason we know it's a permutation is because we only use swap.
Or anything about the order of the elements inside D star.
Yeah, it doesn't say anything. D star, it doesn't, yeah, and the order could have changed.
Immediately looked at this, I would think that what I did was I kept D star in the same order, and I moved the location of C relative to D star.
Yeah, and that's kind of a limitation of the representation. It doesn't tell you that you're changing orders and stuff. But nor, you know, in the actual implementation, or in the procedural code that you copy this from, the orders also change too. It's no different from what's happening over in the procedural world. But the representation doesn't give you any idea that the order is changing. Now, if you had something that was ordered, you would definitely know, because you wouldn't be able to push that D back into the beginning of the ordered D.
So if I was using the ordering hat.
Yeah, if you're using the ordering hat, you'll definitely get stuck with this. You couldn't use this. I couldn't use slide on something. You know, I had to, you know, in the Quicksort. Right, let's go back. Let's change. We really need to do something. Let's change Zen mode off. Go back to Quicksort. In Quicksort, right, I had to do the slide here. I couldn't do the slide down here. Right? I had to do the slide while it was still star. Because if I did the slide down here, right, I would have gotten in trouble. But you would also have gotten in trouble if you did the swap before you did the recursive quicksorts. After you did the recursive quicksorts too, in the canonical procedural version, right? So this system, you know, kind of protects you from getting in trouble, in some sense. Okay.
There was a place where we partitioned like things that are less than.
Yeah.
The pivot and greater than. I didn't see any like comparator operator. How do we?
Right. It's this one, so we're in the right place. Right. So it's all kind of wrapped up in this pivot operation. So rather than do the comparisons, we say, okay, this pivot operation takes some specified A, in this case, this first A over here, and it pivots around. It pivots the rest of the representation around that A. And by pivot, we mean the comparison. So in the definition of A0 is less than or equal to A1, and the definition of A2 is greater than A1. But it's sort of, it's hidden from you, right? Because what we really want is just this, so we can do the partition. So I had, you know, the pivot operator is complete magic, so. Go ahead again.
So yeah, I think in the example for Quicksort, if you could pull up like an example, there was like a bunch of red dots, but we only went through one line of them. Was it a whole box?
Oh, sorry, that was the recursive calls. I put them on the screen.
Okay.
So I put the recursive calls on the screen because I wanted access to them quickly, and then I had to delete all the end leaves where it was empty because it was too much. Sorry about that. I should have explained that, right? There's no loop there, right? But Quicksort's recursive is kind of a loop, so you might want something there to sort of navigate the other iterations. It's self-recursive, let's put it that way. So it's even more recursive than normal recursive methods. John.
So it's crazy.
Thank you.
It's praise for me, right?
Right.
And I don't want to talk about whether it's good or bad. What I want to do is ask you, the future you of a week from now, what is it that you learned from this experiment that was surprising or changed your perspective?
I think I'm not a theoretical person. I'm not like Omar, right? I always thought concrete values would give me everything. I don't do types. I mean, static types are fine, but too much static typing is bad, right? I actually learned that I was just looking at it wrong. That these things are actually types, right? Or to some extent, I was just doing my types wrong, right? So I have a much more appreciation for abstract formal representations than I did a year ago, for sure, right? Because I can do something cool with them now. Before I couldn't do anything cool with them. Now I can do something cool with them.
So you're saying this is a language other than types of abstractions that you weren't aware of before?
Well, yeah, exactly. It was sort of like a new use for abstraction, for formal abstractions that I wasn't aware of before. That it actually is pretty cool to me, right? And also I learned how to sort of get rid of the branching using colors. It's just to linearize things, which is kind of cool.
So follow up then, is this, and you can't know this, it's an unfair question, but is this just one special case because regular expressions are a nice little formalism, or is this opening up a vast space of?
That's a good question. I mean, usually things don't work at all, or they work. They don't just work for a nice class of problems and then stop working, right? And that rarely happens. So it's. But on the other hand, I can't see a way forward to do 2D stuff or to do my own programs, right? Which is kind of I almost gave up because I realized 6 months ago or 8 months ago that I couldn't take this forward, right? That all I could do was quicksort and reverse and some other special cases. But it was just such a beautiful thing that I had to push forward and see it through to the end. And no, I don't think you can. I don't want to say ever, and I'm not like I have a new appreciation of formal abstract representations, but I don't have a deep understanding of them. Maybe I'm just missing something really obvious, some Hilbert space thing or whatever.
Category theory.
Yeah, category theory that will take me through and actually allow me to do more. But my feeling is that the future, the next thing I'm going to try is going to be something that combines both approaches.
Both meaning what?
Concrete and abstract approach, because I'm really itching to get something that I can actually use for my own programs. So I feel like I learned a lot, but it might be a dead end, or it might be an end where some of the concepts can transfer, but not all of them.
Thanks.
So you have this very concise way of representing these types. Have you thought about program synthesis? Because in some cases you have the input, you have the output. Synthesizer could give you a very short program that could get you from your input type to your output type.
The only way I could think of that is using some kind of hill climbing or directed program modification, and this is not. There's no hill to climb here.
Well, not for Quicksort, but some of the other ones that you're doing.
Well, some of the simpler ones, yeah, but in general, no. And it's the same problem with the merge, right? The reason why I'm not doing the merge automatically, the reason why we're not, go back here, select something else. Let's do partition, right? The first version I had, I don't know if Jonathan probably remembers it, right? I had a first version that didn't have the colors and didn't have. And try to do the merges automatically, right? So I would try to sort of infer A star and B star automatically when you did unloop and not require the things to match, but it would actually say, okay, you can loop to this location, but we have to add an A star and a B star here for you to loop, right? That is very difficult, even for that case, which is very simple, right? So I don't have a lot of faith that fancy algorithms will push this forward. But I don't think I don't think they're needed, right? I think if you have a clear way of manipulating the representation to get what you want, then you don't need program synthesis. You just need to do you just need to massage it to what you want, and then you're done. Right? That's the whole Ultron thing. It's not my style. I'm just looking for the Iron Man experience here.
I guess I'm the robot.
Yeah.
Well, maybe not. Yeah. Okay. Come on.
So I'm curious, I mean, so the programming language here is this kind of stack-based language.
Is it stack-based?
I don't know, I mean, it looks like you're kind of talking about what's currently...
It's basically in place mutation of an array,
Okay.
of one array.
Okay. I was curious, I mean, I like the idea of manipulating abstract representations, but I wonder if you thought about what it would look like in a more conventional procedural or functional language setting. I can imagine the functional quicksort or partition function.
Yeah, that's kind of what I was alluding to in my future work thing. Right? I want to try to sort of do some of this in a normal language.
Yeah.
So that you still get some abstract feedback about what you're doing, and maybe you get a concrete feedback too when you can't have abstract feedback. But I haven't done any of the work yet, so I haven't really come up with any sort of shape for that.
Yeah, I mean, there's work on symbolic evaluation, but I don't think it quite gets you what you want.
Right.
Exactly.
Right. I mean, you could take work like on predicate abstraction and then abstract interpretation, where they're trying to figure out, the merges. You're trying to figure out A star and B star automatically, from straight line code, right? And maybe there's something we could do where, maybe automatic inference, maybe we could do manual inference, and maybe that's easy. Maybe that would work really well.
Just some side related to that. There's a little theorem provery flavor here about what's going on, right? You know where you start from, you kind of know where you want to get to, and you're just trying these things in the middle to see if they get you closer and closer.
Human theorem prover.
Right.
Yeah.
So, I mean, in some ways, the stuff, that diagram that you have on the right, almost looks a little bit like a proof tree, right? You start here, you open up, and then you come back down smaller and smaller until you get to what you want. Right? If you annotated those nodes on the right with the intermediate results that you have, and that starts to look a bit like a proof tree.
Well, yeah, that's basically my previous version where I didn't have the colors. My previous version was this with this stuff and mixed in with it, right? What the colors allow us to do is have you just manipulate this. Right, so it's actually, the linear representation is very useful. I guess we're done, so if anybody has any more questions, I'll hang around afterwards.
Does anyone else use this other than you?
No. I don't think anybody else could, unless they wanted to use it for Quicksort. Variations on Quicksort, and maybe bubble sort in the future. Bubble sort is actually really interesting, but I don't have everything in place to do that yet. Thanks.